Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome again to this chapter 18, passive filters. Now, we're talking about section number 2 of this chapter. In this chapter, we will take the first example of filters, of the passive filters. The first example of the passive filters is the low pass filters. We're talking about first order circuits, and we are going to touch a little bit on this concept and try to explain it from very shallow concepts. We're not going to go in depth in that filters design. So we will try to see the equations, we try to see the circuits, we're trying to see the body plots for the magnitude and phase. Okay, let's start.
Okay, so now let's start with these low pass filters. So what is filters normally? The filters are a very useful tool that will allow certain signals to pass, and some of the signals will not be passed. So now we're talking about frequency part. So it will allow certain range of frequencies to pass, and it will reject another part or certain frequencies, and it will stop these frequencies and it will not allow it to pass. So there are two types of filters that we're going to cover. In this section, we'll talk about the low pass filter, LPF. What we're going to discuss in the LPF, we're going to see the magnitude response, frequency response, and because it is complex numbers, there is two parts, magnitude and phase. So we're going to see the magnitude part. So again, party plot, similar to what we've seen before. Then we're going to see a circuit of that filter, how it looks like, what is the RCL component of the circuit, and we'll take very simple circuits. It is the first order, so basic circuits, and we will see the equations. Third, we will see what is the critical frequency, how we can calculate the critical frequencies. Then we're going to see the second part of the complex numbers, the phase response. We will see the body plot and see the equation. So simply, the magnitude body plot equation, the phase body plot and equation. Then the critical frequency. Okay, this is how a low pass filter looks like. So this is a low pass filter where this is the voltage input and this is the voltage input and this is the voltage output plotted against the frequencies. Now this is body plot, so this is a logarithmic scale of frequencies, and this is a decibel point, or it is a linear scale, so semi-log plots. Now here is the magnitude of the output voltage. So we're talking about the magnitude part of the output voltage. So this is the complex numbers. We have to find out what is the magnitude and then plot this magnitude. In fact, these part of frequencies, this range of frequencies will be passed. So all the frequencies from this point to this point will be allowed to pass. And this is the range of frequencies. So after FC, all these values will be rejected. So simply, the critical point or the checkpoint for us is the FC. Whatever below FC will be passed, whatever after FC will be rejected. Actually, this plot here shows that how the output voltage behaves as the frequencies change. So now the magnitude of this signal of this voltage is almost equal to the magnitude of the input voltage. So V out here is equal to Vn at this range. As we increase the frequencies, at some certain point it will start decaying, it will go down. So as we can see here, at a certain range, this will go much lower than the V input. So we can say that in this range the output voltage is there. So is like the output voltage is working. But after this critical frequencies, there is no output voltage. It is much lower than the input voltage. So in this range, we can say that this is not working. So the circuit is not working. So simply, the filter is a place where certain frequencies can make the system working. After that certain frequencies, the system will turn off. So here is the system is on, and here is the system is off. So only with this range of frequencies, the system will work, and after that, it would not work. So this range at which the frequency is passed is called the pass band. So simply it will be this frequency minus 0, so it is the FC, the length of this band. And as you can see here, the critical frequency, at the critical frequency, the voltage output will be equal to 0.707 of input voltage. So in other words, 70% of the maximum of the input. So this formula, you need to remember this formula. At the critical frequency, V out will be equal to 0.7 of the V. And if you plug these numbers in the previous equations that we've seen, you will get minus 3 dB. If you want to calculate the decibel of that ratio, which is V out over Vn, V out over Vn will be equal 0.707. So if you plug these numbers, 20 log V out over Vn, so 20 log 0.707 will be equal to minus 3 dB. So how it looks like, what is the circuit? So we can construct an LPF, low pass filter, from either RC or RL component. Now, if we want to see the magnitude of the output voltage at any frequency, we can derive the equation through voltage divider. Let's see. Now, this is the voltage. This is a low pass filter, and this is the input voltage, and this is the output voltage. We're taking the output voltage across the C. Now, if we apply voltage divider to find what is V out, we will get this equation. Now, we're talking about the magnitude. So simply, you will have the Z, C, and the impedance for R will be equal to R. So if you calculate ZC over the total will give the voltage output shown over here. Now, finding out what is the magnitude of that complex numbers, you will get this equation which is given for you here. Okay, now let's see whether this will be a low pass filter or not. Let me use this ink. So at a low frequency, similar to DC, this will act as an open circuit. So there will be no C over here. So the entire V here will be transferred to V out, because there will be no current passing through this R. So here I will be equal to 0. Therefore, the entire, at low frequencies, the entire voltage went to the V out. Then if we look at the RL circuits and we do the same voltage divider, this will be XL and this is R. So if we calculate the Z, L and R, want to find out what is the R, the voltage over the R, V out, it will be R over ZL plus R. And if you find the magnitude of it, you will get this equation. Now let's test again using the same concepts. So at low frequency, this will act as if it is a short circuit. So when this is a short circuit, the entire voltage will be gone completely over the R. So the V out will be equal almost to V in. That's it. Now, how to calculate the critical frequency? In fact, the critical frequency can be calculated by setting X equal to R, whether it is XL or XC. In that moment, we know that V out is equal 0.707 V in. Then plugging these numbers in the previous equations, we will find out that for both circuits, for RC circuits, as well as for RL circuits, the FC is given by the following equations. This is for FC and this is for RL. So this is RC circuits for the capacitors and this is for the inductors. So you need just to remember these two equations to know what is the critical frequencies for the circuit. Now let's take an example. For the shown low pass filters, an input voltage of 10 volts is applied. Determine the critical frequencies. Using the previous formula, FC is equal 1 over 2 pi RC, you just plug these numbers and you will get that the critical frequency is 339 Hertz. And this is similar to the previous sections. Now, if you want to calculate what is the voltage output at that frequency, there is two alternatives. The first one is to analyze the circuit, find what is ZC here, and apply the voltage divider, and then find what is V out, which is a little bit lengthy way. Second way, which is much shorter, you just apply V out equal 0.707 times V in at critical frequency. And here we go. V in is 10, so the V out will be 707. Okay, now moving to the phase response. The first order RC circuits, as we've seen here, now we're talking about first order, we have very simple circuits. Only one R and one C at RC circuits, and one R and one L, at the RL circuits. So in these circuits, the output voltage lags the input voltage. So it is a lag network. And the critical frequencies the phase shift at the critical frequencies will be equal minus 45 for both circuits. If we want to plot the phase response, here we go. This is the shape how it looks like. So it will start from 0 and it will slowly go down till it reach minus 90. And here is the two formulas, one for RC and the other for RL. Yeah, that's it.
Okay, Alhamdulillah. Now we finished the second part of this chapter, which is LPF, low pass filters. We have covered the magnitude response, we've covered the body plot, the first order circuits, the equations, we checked the critical frequencies, how we calculate them. Then we have touched on the phase response and the plots and the equations. The next section, the last third sections of this chapter, will talk about high pass filters. It will be not big difference from what we've seen here. We will go through similar things. Thank you for watching, and let's see you at the third section.